About thermochemistry. This will be sections 6.1 and 6.2 in your textbook. We're only going to very briefly touch upon a few things in here just to help make our lives a little easier when we get later on in the semester. You will only have to, for this portion of the course, do qualitative kind of analysis of the thermochemistry. You won't be doing any actual math or calculations. So I'll be showing you a few calculations just to kind of put some, perspective on things, but you won't be solving them. So real quick, when we're talking about thermochemistry, we're talking about energy, and we need to think about what energy is. So obviously, energy comes in a lot of different forms. Chemical would be something like what our muscles do. So when we eat something, which helps give us energy to move our muscles, that's a type of chemical energy transformation, versus something like photosynthesis or chemical, how we burn fossil fuels for cars, or electrical, which you could also use for a car. So there are a lot of different types of ways energy can be transformed. However, it's always going to be conserved. So we have this concept of the law of conservation of energy. Energy can be converted from one form to another, but is neither created or destroyed. And that if we looked at the energy of the entire universe as a whole, we'd be talking about a constant. So the good way to think about this is kind of go back to your childhood, the circle of life, Simba. Plants get energy from the sun, and then grazing animals eat the grass, and that gives them energy, to which we turn around and then eat those grazing animals and get energy from them. So there was a lot of different transformations of the energy, but at no point did we lose any. So there's two different kinds of energy. This may seem very physics-like to you, and it does play a big role in physics as well, but we have the idea of potential energy and kinetic energy. Potential energy is the possibility that energy could do something. So in terms of chemistry, potential energy is held up in the bonds between atoms. That's where the energy is held. It can also result in attractive or repulsive forces. So in an ionic bond, what's holding an ionic bond together? It's the electrostatic potential between the positive charge of the cation and the negative charge of the anion. So there's a potential energy there. In covalent bonds, it's the energy associated with the two electrons being shared, or two or more electrons being shared between the bonds of the atoms. Kinetic energy is energy in motion. This is, balls rolling down hills and pens falling off of desks and all the ings, right? And kinetic energy is typically described by this equation here. So we did talk about the idea of that energy gets transferred, right? It's not created, it's not destroyed. In terms of chemistry, where we see that happen is when we're talking about temperatures of things. So think when you're in lab and you boil something, or you mix two things together and they get hot. We're going to start having different vocabulary. Up until now, you may have interchangeably used the words temperature and heat. But now we need to start thinking about them in terms of temperature reflecting the random motion of particles. So, as the temperature increases, the particles start to move faster. There's nothing organized about it, it's just the random motion of them. And that heat would be the transfer of that energy between two different objects at different temperatures. So, a hot plate sitting on a cold countertop or something like that. So again, when we're talking about this, we're talking about the pathways that these energies are taking. That's about the extent at which we are going to really discuss that for the purposes of our class right now. So again, the only other thing that I want to bring up is heat and motion. This will be something you'll see in labs and stuff like that. But just for a convention of everyone understanding the direction that we're talking about with the transfer of heat, we're always going to go from hot to cold. It's just a convention that we use. That way when you do the math, we're not worried about which direction we're going with that. The universe, right? When we're talking about systems, we could be talking about something as small as, what's going on inside a little closed beaker, or we could be talking about the whole universe. So the system is the thing we're observing, and the surroundings would be everything else. Sometimes the surroundings are everything else, and our system is the, known universe. And sometimes the system is something, like we said, as simple as an enclosed beaker or something like that. So the big thing that we want to take away from thermochemistry in 6.1 is the concept of endothermic and exothermic reactions. And this is that flow of heat that we were talking about earlier. So exothermic reactions, they're reactions that result in the evolution of heat. So the energy is flowing out of the system. So remember, we're going from hot to cold. So the heat that was in the system is leaving the system to the surroundings. An example of this would be a combustion reaction. So think about what happens when something explodes or catches on fire. It gives off heat. It's not 100% correct. For the purposes of our class, it will suffice. But it's not a hard, fast rule to say that an exothermic reaction, heat is a product. It's a simple, nice definition, and for Chem 200 it works. Just be prepared that if you go further on in your chemistry career, you might not be married to that saying forever. An endothermic reaction is the opposite. It's a reaction that absorbs energy from the surroundings to make something happen, to make the reaction happen. So this example that most people are familiar with would be if you've ever had a first aid kit with one of those emergency cold packs in them, where you break the insides of the two containers together and it gets cold. What's actually happening is there's a reaction, chemical reaction going on inside the bag, and for that reaction to occur, it needs energy. So it's going to draw energy in the form of heat from the surroundings into the reaction, making everything else around it feel cold. So in terms of how you can memorize this, is exo has kind of like the word exit in it, so the heat is leaving the system, and endo kind of looks like in, so things are entering, the heat is entering the system. Again, right, this concept of energy is conserved is an important one. So energy gained by the surrounding in an exothermic process needs to be lost by the system. So the same amount of heat that is generated that is leaving the system, that's the same amount of heat that was lost by the system when it was doing it, and vice versa. So if a system that is endothermic requires a certain amount of energy going into the system, that's how much is lost by the surroundings. That may seem very obvious, but again, when you get further on in 201 and things like that, mathematically this will become important. So again, this is just kind of a pictorial representation of what we just said. So here is an exothermic process, right? So here is the energy. Here's our reactants. We have methane burning with oxygen. And here are the products that come from that, right? So you can think of this as a chemical reaction. O2 plus CH4, 2 O2s plus 1 CH4 yields 2 H2Os and 1 CO2. Right, if we had like a chemical equation. And the difference in energy between the products and the reactants is this amount here. And that difference in energy is equal to the amount of heat that is released by the system. That's all we're saying with that. The same could be said of an endothermic reaction, right? In an endothermic reaction, energy is absorbed into the system. So if our chemical equation would be something like N2 plus O2 yields 2NO. The difference in energy between the reactants and the products is the same as the amount that is absorbed from the surroundings. I'm going to skip over this for now just because you know, you guys have a lot going on. You can read this. Again, we are not going to be doing any work or change in energy equations. So you can kind of skip this for now. You will have more fun with this in Chem 201. So again, the one thing that we want to bring up is this general concept here, this qualitative kind of concept, that the energy change between the products and the reactants, if the energy change or if it's an exothermic reaction, the change in energy will be less than 0 or a negative number, and if it was greater than 0 or a positive number, it would be endothermic. The last topic we're going to touch upon is the concept of enthalpy. Again, we will see enthalpy, H, we use H as the symbol for it, or delta H if we're talking about the changes in enthalpy, a little bit later on this semester. So we just kind of want to bring it up again for you guys so that you see it now and, you know, can kind of understand it later. But under a constant pressure, right, the delta H will equal the energy flow. So that's kind of where we're going with this. So that heat flow that we talked about earlier, whether it's leaving the system or entering the system, that will be under constant pressure, which is what we'll be looking at essentially. That will be equal to this enthalpy change. And again, you don't need to worry right now about any of these equations. We just want you to have a general qualitative understanding of it. So that's what we're looking at right here. So again, when delta H is positive, we'd be looking at an endothermic system, and when delta H is negative, we'd be looking at an exothermic system. That's about all you really need to know from our Thermochemistry Chapter 6 for Chem 200. You will go into so much more detail with this in 201 and later on in your chemistry path. So we're just kind of bringing some of these things to light so that you have kind of an exposure to them for a first time. So if you have questions with this or concerns, please let me know. Like we said, there won't be really any math involved with this. This will all be qualitative.